Okay, this is the Algebra 1, Chapter 12, Section 8, Probability of Compound Events. The objectives of this lesson are to find probabilities of mutually exclusive and overlapping events, and to find probabilities of independent and dependent events. So we have some vocabulary words here. So mutually exclusive events. When two events have no outcomes in common, the events are mutually exclusive. If A and B are mutually exclusive events, then the probability of A and B, if the probability of them both happening are zero, right? If they're mutually exclusive, so they both can't happen at the same time, right? If you flip a coin, you can't have heads and tails land, right? So the probability of landing heads and tails in one roll is zero. When events have at least one outcome in common, they're overlapping events. So you need to determine whether the two events A and B are mutually exclusive before you can find the probability of A or B happening. So if they're mutually exclusive and they don't overlap, then the probability, you can just add them. But if they are overlapping events, then you have to add the probabilities, but then the probability of them both happening are included in both of them. So it would be double counted if you don't, and so you have to subtract one of them. Okay, so let's see an example of this. Suppose you spin a spinner that has 20 equal-sized sections numbered from 1 to 20. What is the probability that you spin a 2 or a 5? Okay, so in a spin, you can't spin a 2 and a 5 at the same time. So these are mutually exclusive. So the probability of 2 or 5 is going to be the probability of 2 plus the probability of a 5. In this case, remember, probability is number of successes over number of possibilities, or number possibilities. In this case, we have 20 possibilities, and you can the success would be, in this case, a 2, and there's only one 2, so it's 1 out of 20. And then the same thing for 5, there's only one 5, so this is 1 out of 20 plus 1 out of 20, so the probability here is 2 out of 20, which is 1/10. Okay. And just so you understand this, you can also think about it how if you just had number of successes over number of possibilities, right? 2 or 5 would be 2 successes, so it would be 2 over 20, right? So that's where that comes in. That's another way to think about it. But these are mutually exclusive, so you can add them separately. The second question says, what is the probability that you spin a number that is a multiple of a 2 or a 5? So let's see, out of 20, let's think the probability, let's see, successes for multiple of 2 in this case would be, let's see, successes. Multiples of 2, you have 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20, right? Out of our numbered 1 through 20, those are all our successes for multiples of 2. For multiples of 5, you have 5, 10, 15, and 20, right? So you can see that these probabilities overlap, right? By the 10 overlaps here and the 20 overlaps here. So if you just added up everything, right? When there's 10 here and there's 4 here, you can say, oh, the number of successes is 14. So it should be 14 over 20, right? But then you see how you're double counting the 10 and the 20? The probability of that happening, landing on a 20, doesn't change. So these are overlapping events. So the probability of multiple of 2 or 5 is going to be the probability of a multiple of 2 plus the probability of a multiple of 5. And then since they're double counted, you have to multiply the probability. It's a multiple of 2 and 5. Okay, so the probability of multiple of 2, we have 10 here. So there are 10 out of 20. And then in this case, there are 4 out of 20. But remember, the probability isn't 14 out of 20 because you've double counted these. So you have to double count the 2. The multiples of 2 and 5 are 10 and 20. So there are 2 successes in this case. So you subtract out the 2. And this becomes 14 minus 2 is 12 over 20, which is, divide them both by 4, 3/5. Okay, and again, if we just think about it, how we learned it, just a number of successes over possibilities, we could just count the successes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's not count the 10 and the 20, 11, 12. And you can see it's 12 over 20, so that still holds there. Okay, and you can do them both ways. Okay, so try these two on your own. I can leave the formulas up there too. Suppose you roll a standard number cube. I drew a nice picture for you to see, right? There's 6 sides and it's numbered 1 through 6. What's the probability that you roll an even number or a number less than 4? And then what is the probability you roll a 2 or an odd number? So press pause, try these on your own, and then check back for the solutions. Okay, hopefully, I just did the first one first. Hopefully for this first one you get 5, 6 probability, right? That's because even numbers the successes are 2, 4, 6. And then the successes for less than 4 are 1, 2, and 3. So the 2's overlap, so this means they are overlapping events. So it's going to be the probability of either of them happening are going to be the probability of even plus the probability of less than 4, and then minus the probability of even and 4. So you're not double counting this 2. So the probability of even is 1, 2, 3 out of 6. The probability of less than 4 is 1, 2, 3 out of 6. And the probability of even and less than 4 is there's just one that overlaps. So we're going to subtract 1 6. So this is 3 plus 3 minus 1 is 5 over 6. This is 5 6s. And then you can also double check that you count 1, 2, 3, 4, 5 unique different choices here. So 5 successes out of 6. Okay, so press pause and try B. Okay, and then hopefully for this one you got the probability was 2/3. And these were mutually exclusive, right? If you roll a 2, that's just successes are a 2. For an odd number, successes are 1, 3, and 5. Nothing overlaps. So the probability of 2 or odd are just the two probabilities added together. So 1/6 for the 2 and 3 6s for the odd number. So 4 out of 6, which is 2/3. Okay, so a little more notes here. So in a standard game of checkers, there are an equal number of red and black checkers, and the diagram at the right shows possible outcomes when randomly choosing a checker, putting it back, and choosing again. So the probability of getting a red on either choice is 1/2, right? Because you either have a red or black, so 2 choices and 1 success. The first choice or event does not affect the second event because you put the first checker back. So the events are independent. So 2 events are independent events if the occurrence of one event does not affect the probability of the second event. Okay, so think about that, right? The first choice is red or black, then you can get red, then the second choice is either red or black, and the probability is 1/2 each time. It's because they're saying before you make the second choice, you put that checker back, so there's still the same amount of chips. So the probability of 2 independent events happening are probability of A times probability of B, if A and B are independent. And so let's see how that works. Suppose you roll a red number cube and a blue number cube. What is the probability that you roll a 3 on the red cube and an even number on the blue cube? Okay, so you're rolling them. The red one does not affect the blue one. So these are independent events. So that means the probability of A and B are independent. So it's going to be the probability of A times the probability of B. In this case, A is a 3. So a success, there's only 1 success out of 6 choices on the number cube. And then the blue is an even number. There are 3 even numbers out of 6. So then you multiply these. So let's multiply across. This becomes 3 over 36, which is 1 over 12. So you have a 1/12 chance of rolling a 3 and then an even number. So that would be with 2 rolls. And so it kind of can be set up like here. We have first roll, or red roll, let's call that red roll, and then blue roll. Right, you have 6 choices here, but say you the chance of even getting to this part here is 1 in 6. Right, so you only have a 1/6 chance, and then once you get to the 3, you have a 1/6 chance of getting a 2, a 1/6 chance of getting a 4, and a 1/6 chance. So 3 out of 6 choice of getting these successes. So you already have a probability down to 1/6%, 1/6 of a, not percent, but if that was a percent, 1/6 probability. And then after that, you still only have a 3/6 chance. So you multiply them together. And we can do it like this too. This becomes a 2 and this cancels. So this is 1/12. Okay, so try this next one on your own. You roll a red cube and a blue cube. What is the probability that you roll a 5 on the red cube and then a 1 or a 2 on the blue cube? So these are independent events. So use your probability of 2 of independent events on your own after pressing pause and then check back for the solution. Okay, hopefully you got 1/8 is the probability here. The probability of getting 1/6 on the red. A 5 on red is 1/6. The probability of getting a 1 or 2. Here you have 2 successes out of 6 tries. So then you, because they are independent, right? Red and blue are separate from each other. They don't affect each other, what they roll. And so you can just multiply them together and you get 1/18. Okay, problem 3. You choose a tile at random from these tiles here. You replace the first tile and then choose again. What is the probability that you choose a dotted tile and then a dragon tile? So because you are replacing, these are independent, so you can just multiply the 2 probabilities together. So let's call them A and B, or let's probably call them dot. Probability of dot times probability of dragon. So let's just find out the successes of dots are 1, 2, 3, 4. 4 successes out of 3 times 5, 15 tiles. And then you replace it, so you still have 15 tiles. And then dragons are 1, 2, 3, just 3. So then we can just multiply them together. Let's make this a little easier on ourselves and get rid of this 3, make that a 5. And then this becomes 4 over 75. Okay, so 4/75 of a percent. Sorry, didn't mean to say percent. 4 over 75 probability. 4 out of 75. Okay, right, you can say it like a 4 out of 75. Or you can actually do 4 divided by 75 and turn it into a decimal here. And this is like 0.0533 repeating. So it's about 5.3%, which might give you a better idea about what that actually means. Okay, so try this red star. It's going to be using the same tiles here, and see if you can figure out the probability that you randomly choose a bird, and then after replacing the tile, get a flower. Press pause, try this, and check back. Okay, hopefully you got 2 out of 225. It's because these are independent events since you replaced, so you just multiply probability of the bird times probability of the flower. There's 2 birds, 1 flower, and there's 15 tiles. And since you replace it, there's still 15 tiles here. When you multiply that out, it's only 2 out of 225. So that's a small probability. If you turn it into a percent, it's 0.89%, so even less than 1% chance that happens. Okay, and then, so we're still not done. Exciting stuff, dependent events. So we talked about independent events, now we're talking about dependent events. They are dependent if the occurrence of one event affects the probability of the second event. So for example, in problem 3, if you do not replace the first tile before you choose another, that this changes a set of possible outcomes, right? If you don't replace, then this after you take a bird, right, there's only 14 tiles left. So the probability of getting a flower wouldn't be 1 out of 15, it would be 1 out of 14. And that's what you'll see here. The probability of A then B in a dependent event is probability of A happening, and then the probability of B happening after A has already happened. Interesting. I've never taught this from this book before, but normally in probability, you would see it written like this: probability of B given, and they call it given that A occurred, and you'd see this slash. But they're using, I guess, simplified vocabulary here. But as you move on in math, when you get to probability and statistics, you'll see this. It's called given. This is called B given probability of B given A occurred. Okay, so let's see what this one says. Suppose you choose a tile at random. Here's the tiles again. Without replacing the first tile, you select a second tile. What's the probability that you choose the dotted tile and then the dragon? So let's see, we do probability of dotted, and then we're times, it's the probability of dragon, given that we've already picked dot. Okay, so probability of a dot, again, there are 1, 2, 3, 4 dotted, and there are 15 tiles. Now we've taken away a dot. Okay, so now there are only 14 possibilities. So the denominator here changes, and we still have 3 dragons. Okay, then you just multiply across. We can cancel some stuff to make this math a little easier. This 3 cancels with this 15 and leaves a 5. This 4 becomes a 2, and this becomes a 7. So that makes our math 2, and then 5 times 35ths. Which if we did in a calculator becomes 0.057, so about 5.7% chance. Which is slightly higher. Remember in the first one, you may not remember, but the other one, this problem 3, we had about 5.3% chance. So there's slightly better chance that you get this because in this case there are less choices. So you have less chance of not getting the dragon in the second one. Right, so that's why it's slightly higher. There's slightly bigger chance that you choose the dragon in the second choice than you did in the first one. Because remember, when you replace it, this becomes a 15. Okay, so try this next one on your own. What's the probability that you randomly choose a flower and then without replacing, you get a bird? So press pause, try this on your own, and then check back for the solution. Okay, hopefully you got 1 in 105 probability there, which is, again, a little bit less than 1%, but higher than the other one. Remember, the other one was 0.89%, so this is a 0.95%. And that's because, right, when the probability of choosing the bird, given the flower, was already gone. So there were 14 choices, so it's a little bit higher chance that you pick that bird on the second try. Okay. All right, last problem. There are 1 freshman, 2 sophomores, 4 juniors, and 5 seniors who received top scores in an essay contest. To choose which 2 students will read their essays at a town fair, 2 names are chosen at random. What are the probability of a junior and then senior? Okay, so remember this is going to be probability of junior, then senior. And so they are dependent on each other, right? When you pick the senior, one person's already gone. So this is going to be the probability that you pick a junior first. Then you're going to, it's the probability that you choose a senior given that a junior was already chosen. Okay, so the probability there's a junior. So there are 1, 3, 7, 12. Okay, so we have 12 students. And so that's their possibilities. And the chance that you pick a junior is 4 out of that, right? There are now 11 students left. Right, and there are still 5 seniors who haven't been chosen. So then your successes are 5. So then we can just multiply this across. All right, this will cancel to 1/3, and so this is 5 out of 33. And then if we just want to see that as a percent, this is about 0.1515 repeating. Actually, that's exact. And then, so that's about 15.2% chance that the junior is chosen and then a senior. Okay, so see how that works? Try this next one on your own, press pause, check back for the solution, and then we'll be done. All right, hopefully you got the same thing, 15.2%. You can see really what happens is, right, there's 5 out of 12 at this point, because it's the senior, and then there's 11 in the second choice, but there's still 4 juniors. So these numbers just got switched around. So you're going to get the same thing here. Just a side note, if it said what's the probability a senior and then another senior were chosen, right? It would be 5 over 12. But then for this probability of a senior, given that a senior was already taken, right? There's 1 less student, so the bottom changes 11. There's also 1 less senior, so this would be 4 instead of 5, right? So we have to take that into account too if that comes up. Okay, that's it. Enjoy. Here's your practice problems.